All right, everyone, we are going to go over the next section in the notebook. Make sure you copy down everything. There'll be some problems that I've left blank that I'll just give you some hints and you will be able to work those out on your own. Otherwise, we want everything to be written down and organized basically the same way as I have it here. When we deal with circular motion, we'll be dealing with two different types of situations: uniform circular motion and non-uniform circular motion. So in uniform circular motion, you're going to be going at a constant speed in a circle, and not slowing down or speeding up. In non-uniform motion, you will be going in a circle, but you might be speeding up or slowing down as you go around it. That could be similar to like whirling a bucket of water. You're holding a bucket of water and you're whirling it in a vertical circle. As the water gets to the top of the circle, it's going to slow down. When it gets to the bottom, it's going to speed up. But if you were to swing that bucket of water fast enough, you could swing it around and the water would never actually dump out of the bucket and get you wet. Another example of non-uniform circular motion might be a car that's going around a track. And as the car goes around the track, the car is going to speed up, right? You should know the relationship between the radius of the circle and the speed or the rate of revolution, and how those are related to the magnitude of centripetal acceleration. You should be able to describe the direction of the particle's velocity and acceleration at any instant during the motion. And for uniform circular motion, the velocity is going to be tangential and the acceleration is going to be towards the center. We call that the centripetal direction. Parts C and D here actually came from another set of standards, not for uniform circular motion. So these could kind of apply to other motion as well that's not uniform. You want to be able to determine the components of the velocity and acceleration vectors at any instant and sketch them or identify graphs of them. Analyze situations in which an object moves with a specified acceleration under the influence of one or more forces, and be able to determine the magnitude and direction of the net force. This would include going around a circle and speeding up or slowing down. And then some examples of how you expect to do that in part D. Motion in a horizontal circle, which wouldn't always, but a horizontal circle is more typically going to be uniform motion. In a vertical circle, it's less typically uniform, and more often the speed is going to be changing, and we would call that non-uniform motion. It's still circular, just that you're speeding up and slowing down. Within circular motion, for uniform circular motion, just some facts to keep in mind. Your speed does not change. Acceleration is purely centripetal, which means it's always directed towards the center. That's what centripetal means, towards the center. It's just a direction. It's exactly like saying horizontal or vertical. And we can have horizontal or vertical forces, and we can have centripetal forces, but centripetal is a direction that a force points. It's not an actual type of force. If you remember at the beginning of the unit, when we went over types of forces in that video, we didn't ever talk about centripetal. We talked about like friction and tension and gravitational, and then there was electromagnetic or nuclear strong, nuclear. Those are all types of forces. And some of those are just applications of electromagnetic. But centripetal is definitely not a type of force. It's a direction. And if you have a centripetal force, something else is the cause of that force in that direction. Centripetal acceleration is v squared over r. And if you have centripetal acceleration that's more or less than v squared over r, you're going to depart from circular motion. So in that example of swinging the bucket of water over your head, if the centripetal acceleration from gravity was more than v squared over r, that's when the water falls out and gets you wet. The sum of the tangential forces, if there are any, will add up to 0 when you're in uniform circular motion. Now, in non-uniform circular motion, the tangential forces will not add up to 0. The tangential forces are the ones that either are going to be with or against your velocity. And we know when we have a net force with or against our velocity, we will speed up or slow down. So tangential acceleration will not always equal 0 there. Well, it won't ever equal 0 because you're changing speed. And again, if the centripetal acceleration is more or less than v squared over r, you will depart from circular motion. That part about centripetal being a direction, make a note of it up at the top. It's not a type of force, it's just a direction. In general, for these kind of problems, if you were looking like top down, maybe on a car going around a bend or something, we'd want to use polar coordinates, where you have like maybe a radius and then an angle. The angle is not as important here on uniform circular motion, but the idea is we have a centripetal component and then we have like a kind of a tangential component there. And we'd use centripetal and tangential as our two directions, or maybe if we were like, swinging something in a circle, or we had to deal with friction, keeping a car in place as it goes around a corner, then we'd use like centripetal in the y direction. Centripetal direction will always point towards the center, and I always call towards the center positive. Away from the center is going to be negative. The tangential direction, usually it's easiest to call with the velocity positive and against the velocity negative. If you're going to speed up as you go around the circle, your tangential acceleration would be positive with the velocity, then you speed up. If you are going to slow down going around a circle, then the tangential acceleration would need to be negative. A centripetal force is any force that points towards or away from the center of the circle that you are moving around. So some equations that we'll be looking at, and just some general information about this stuff. Uniform circular motion. The sum of the forces in the centripetal direction is mass times acceleration in the centripetal direction. That acceleration centripetally is v squared over r in magnitude. The direction, of course, is towards the center. The velocity that we have is 2 pi r, which is our circumference of the circle, divided by t, which we call the period, usually a capital T for that, the period, which is the amount of time that it takes you to go around once. And the frequency is related to the period. The frequency is measured in hertz, and that's a measure of the number of revolutions per second, which is the inverse, or the reciprocal, I should say, of the period. So another way of writing our velocity, instead of 2 pi r over t, which is distance over time, we can do distance multiplied by 1 over time. So 2 pi r times the frequency. So a frequency of 10 hertz means 10 cycles or 10 circles per second. In non-uniform circular motion, we are going to be speeding up if our net force points towards the center and somewhat in the direction of velocity. So if I was going around the circle counterclockwise, if I wanted to speed up, I would need a net force that pointed towards the center and in front of me compared to the direction that I'm moving. That means that some of this net force is pointed towards the center and some of it is directed tangentially forwards in the direction of my velocity. If I'm slowing down, the opposite is true, and my net force would point towards the center but slightly behind center compared to the direction that I'm moving. And as always, you pause these as needed to write down the information. Top sticker on the next page, we have a conical pendulum. Why is it called a conical pendulum? Because if you were to trace this out in space, it makes a cone with the chord. So conical having to do with a cone. Fun trivia fact, or maybe not so fun depending on your personality, but hyperbolas, parabolas, circles, and ellipses are all conical sections. That is to say, shapes that you get when you cut through cones. You can make circles, ellipses, parabolas, and hyperbolas when you cut through cones at various angles. So here we have a conical pendulum because it makes a cone shape when it swings around. We'd be going around and round and round and round in circles. We have a tension coming up to this the ceiling there. This might remind you of the flying pig lab that we did last year. Tension opposes gravity and it provides the centripetal force. It does both of those things. The y component of tension will oppose gravity. The y component of tension. Now this theta here is from vertical. If you were measuring the other angle down here, this would not be cosine, it would be sine. But cosine of this angle is going to find us the adjacent side, which would be the vertical side of tension. So this is the y component of tension minus our weight, just another way of saying the force of gravity. So we get T cosine theta equals mg. And then for the centripetal side, sigma f equals mac. We know AC is v squared over r. And the centripetal component of tension is T sine theta. Sine will find us the opposite side, which is the centripetal side in this case. We've got a coin here going, or a little box, I guess, on a turntable. In this case, it's rotating clockwise when viewed from above. We have our weight, we have the normal force, we have friction going towards the center, always towards the center. Here we've got a car going around a corner, weight down, normal force up, friction towards the center. Now, the static friction that keeps both of these in place, the car going around a corner on a flat road or this box spinning on a turntable, the force of static friction is going to be less than maximum if you're spinning at a slow enough speed. The force of static friction will be just enough to provide the centripetal acceleration. If you spin too fast, then the static friction will break and this thing will slide off the table or your car will slide off the road. But if you're spinning right at that maximum speed, then the force of friction will equal mu Fn. And as I just said, the object slips if you spin faster than that maximum speed. So, in both of those examples up there, I've given some numbers here to make this a little more realistic. I said for this car here, we're going to use a coefficient of static friction of 1.1. I don't know off the top of my head if that's typical for tires or not. I can do a quick search here and find out. But I do know that race cars have coefficients of friction that are up in the sometimes as much as 3 to 4 range. So let me see here. Coefficient of friction for tires on roads might be 0.7 for dry roads and 0.4 for wet roads. It says here that some coefficients go as high as 0.9. So I don't think 1.1 is totally out of the question, although it may be unusual. Wet roads might have a coefficient sometimes as low as 0.1, and icy roads maybe even lower than that. So this is a very sticky combination of road and tire that we're talking about here, but not too crazy. We're going to look at the centripetal direction, and in the centripetal direction, we've got, let's find the maximum velocity that we're going to be capable of going around this turn at. So if we're going at the maximum speed, our acceleration is going to be Vmax squared over r. The centripetal force is only friction, which is mu mg. The m's cancel, and we're going to get a max velocity of square root of mu gr. And I said that over here that the track was 100 meters in radius. So when we plug all that in, we get a maximum speed of 33.17 meters per second. That's a, maybe like 70 miles an hour or something. And 100 meters, that may be like similar to a curve that you could be exiting like a freeway ramp with. So 70 miles an hour, kind of quick to be exiting a freeway ramp. You might feel your car begin to slip at those kind of speeds, although oftentimes some of those exit ramps, if they're going to make them that sort of curve, they will also build in a little bit of a bank to them. This is on totally flat ground that we're talking about here. I think I had meant to put a little blurb of text in here about the things that I wanted to find. But if we had a car that was accelerating, here it is over on the left. Our car is accelerating from rest at 3 meters per second squared on this circular track. So we found what the maximum speed is. Now let's find how much time the car can accelerate at that speed until it reaches this speed and slips. So we'll just use some kinematics here to find the amount of time until we get from a speed of 0 up to a speed of 33 with an acceleration of 3. Turns out it takes us 11 seconds, just over 11 seconds, until we're going to begin to slip in this car. Now, if we wanted to figure out how far we're going to drive before we begin to slip, we would have our kinematics equation. We'll just plug in everything that we know. Our acceleration, our velocity squared. We get 183 meters around the track, which was a 100-meter radius, like circular racing track. So we'll get 183 meters around the track before we begin to slip. And if we wanted to think about, like, as a percentage, how much of the way around the track that is it a half turn, 3/4, 1/4, 2/3 of the way around? What we can do is take that distance of 183 and divide it by the total distance of one lap around the track. So if we take the distance we travel divided by the total distance of one lap, we're going to get the percentage of the way around the track we've traveled as a decimal. So this is 29% of the way around. So that's just over a quarter lap before we're going to begin to slip. Here we've got the gravitron on the next page. In this amusement park ride, the ride spins around, the floor drops away, and static friction will keep riders kind of stuck to the wall. Now, in reality, the Gravitron doesn't quite work like that. The actual ride has walls that are like slightly tilted back like this, and the walls have a little platform on them that slides up. So the wall actually slides up rather than the floor dropping away, but the principle is the same, okay? If you spun around fast enough, friction would keep you stuck to the wall even if the floor dropped away. And there have been some rides that have worked more on that principle. I couldn't find any video of them, but I did find some video of the Gravitron, which I will show you. So here is a clip of the Gravitron, and you can a little bit. Who doesn't like screaming kids, right?
Have you?
Okay, so here you can see the ride's beginning to spin. People are already stuck to the wall. There you can see some of the panels that are going to slide up. Those people are definitely stuck to the wall. There's the operator sitting in the center of the ride. Kids having fun. It certainly looks like fun to me. Now, if the ride stopped right now, those people would slide down and crash on their heads. If you were brave, you could stand on the wall. I'll show you a clip of someone doing that in just a second here. So that's the Gravitron. Let me show you a clip of someone standing on the Gravitron. This guy here.
Watch him, bro. He's just stand on the wall.
So the ride's already spinning around, and he's able to stand up because of the circular motion aspect. That's where you wouldn't normally be able to stand up. But this is a little bit early, and the ride is spinning fast. Oops. Circular motion got the best of it. So, there you go. You can hunt down more incidents of Graviton shenanery on the internet if you choose. Our free body diagram for the Gravitron is just three forces. They're all right there in the picture. Gravity down, friction up, normal force towards the center. The normal force provides the centripetal acceleration. The faster you spin, the greater the normal force is going to be, and the greater the normal force is, the more friction becomes. So at some speed, you're going to have a normal force that gets big enough that it provides enough frictional force to counteract gravity. So what's the minimum speed that this ride could go at? Look at the centripetal direction. That's only the normal force, and that's got to equal mv squared over r. In the vertical direction, we are going to have no acceleration because we're stuck to the wall. And we're dealing with static friction, so mu Fn, because we want the maximum value. We want the maximum value because we're trying to find where we're just barely able to stick to the wall without sliding down. So mu mv squared over r, where did I get that mv squared over r? Right here from the centripetal direction. We plug that in, and then we can solve this to find that v equals the square root of gr over mu, and that is the minimum speed that the ride would have to go. If you went any faster than that, then the normal force would be so large it could actually provide more friction than is required to keep you in place. Of course, that won't actually happen because as the ride spins faster and that normal force gets bigger, although the maximum value for static friction would increase, the actual value for static friction will stay the same because it's adjusting itself to however much it needs to just to keep you in place, which is always the same amount, the value of gravity. If you go through a dip in a car, or you've experienced this on a roller coaster perhaps, you go down through a dip, you feel heavier than you normally do. And the normal force is related to your experience of weight. If you experience a greater than normal force, you feel heavier. If the normal force becomes lighter, you feel lighter. If there is no normal force, you might feel weightless, right? Like if the floor was to suddenly drop out from underneath you and it's not supporting you at all and there's no normal force, what are you going to do? You're going to free fall. And do you feel weight when you free fall? No, you feel weightless. Weight is a measure of not just the force of gravity on you, but also it's your experience of weight is related to the surface that's supporting you. So here we've got a dip of radius r. That means the center of our circle is above the car. And the person in the car is going to feel heavier. We've only got two forces, normal force down, or normal force up, gravity down. The sum of the forces in the centripetal direction is MAC, and the centripetal direction is upwards here, okay? Make a note of that. This direction's plus, that direction's minus. So we have Fn minus mg equals mv squared over r. And then we can solve that out for Fn, and we see that it's mg plus mv squared over r, which is heavier than we would normally feel. Normally, we would just feel mg. Here, we feel mg and then some. And you can see that the faster we go and the smaller the radius of the dip is, the heavier we're going to feel. Conversely, if you go over a crest of radius r, we're going over a hill here, so now the center of the circle is below us. And remember, the centripetal direction is always towards the center. So this would be plus and that would be minus, right? That way. Plus is towards the center. So in this case, gravity is going to provide the centripetal acceleration. And when we're about to jump, the normal force becomes zero. Now, when the normal force becomes zero, we're still on the road. If we were going any faster than that minimum speed, then or that maximum speed, if we're going any faster than that, then the car actually catches air. So we take the sum of the forces in the centripetal direction. There's only one of them, it's gravity. Because remember, we want to be on the verge of jumping here. So it's just gravity, and that's going to equal mv squared over r. We solve that, we get the square root of g